A carousel at rest begins accelerating at 0.05 radians per second squared for 8 seconds, after which time it continues rotating at a constant angular speed. Child A is riding on one of the inside horses. That's 2 centimeters from the carousel's axis of rotation. Child B is riding one of the outside horses, 5 meters from the axis of rotation. Parts A and B are pretty straightforward and simple, like straight from the notes, so I'm going to skip those and hope you just know the answers to them already. Look down to part C. When the carousel first starts moving, is child A's acceleration directed primarily toward the center of the carousel or primarily in the direction of the motion? And we just have to remind ourselves here what the center pointing acceleration is and what the acceleration is in the direction of motion. And it is the acceleration that points toward the center is the centripetal, AC, which we have a new formula for now, omega squared r, where omega is the angular speed, and the one that's in the direction of the child's motion as the carousel is speeding up is the tangential or the linear acceleration, which is the r times the angular acceleration, r alpha. So if we look at on the carousel, one particular thing, the AT is that way in the direction of motion. The AC is toward the center, and at any given point in time, those two accelerations form a right angle to each other. So in question C, when the carousel first starts moving, which way is the acceleration pointing? When it first starts moving, it's increasing at a constant angular acceleration. So this tangential velocity right here will stay fixed, at least for the first 8 seconds of the carousel's motion, because that angular acceleration is constant. But the angular velocity, this omega, is gradually building up over time. So when the carousel first starts moving, this omega is a very low value, which means the centripetal acceleration is going to be a very low value. So initially, the AT is going to be much bigger than the AC, so it's going to be primarily in the direction of her motion. But after 10 seconds, remember the carousel stopped accelerating at the 8-second part, so at 8 seconds, it no longer even has tangential acceleration since the angular acceleration has become 0. So at 10 seconds, this arrow no longer exists, and the only acceleration that the carousel has is that AC, the centripetal acceleration, so that's basically the answer primarily toward the center because it's entirely toward the center. In part E, we want to calculate the magnitude of the child B's total acceleration 7 seconds after the carousel starts moving. So to get the total acceleration, we need to calculate both the AT, the tangential acceleration, and the AC, the centripetal acceleration, and then because they are vectors that make a 90-degree angle with each other, you can get the total acceleration, which points in that diagonal direction, by taking the Pythagorean theorem of those two linear accelerations, the centripetal and the tangential. So to calculate the tangential acceleration, you just want to use this formula. The r is given and the alpha is given, so that's pretty easy. For the centripetal acceleration, after 7 seconds, you know the r, that's again 5 meters, and to get the omega, you can just use basic rotational kinematics. So you know that the carousel started at rest, so omega naught is equal to 0. You know the alpha is the 0.05, and you know the time is the 7 seconds. So from that, you can solve for the omega and plug it in for the omega right there. So now you have the value for the centripetal acceleration, and with those two values, you can the tangential and the centripetal, which are roughly 0.25 and 0.61. When you take the Pythagorean theorem with those, you should get a number pretty close to that 0.67, maybe a little bit off due to rounding, and that's fine. And then for part F, we want to calculate the time at which the centripetal acceleration, the AC, is equal to the tangential acceleration because you want them to have the same magnitude. So if we just plug in those formulas and set them equal, we have AC, which is omega squared r, is equal to AT, which is r alpha. You can see that you have an r that cancels out from both sides, and when you did kinematics on these variables, you should have used the equation omega equals omega naught plus alpha t, and since the carousel started from rest, the omega naught was 0, so omega is just equal to alpha t. So if you take that and plug that formula in right here, keeping in mind that the omega is squared, so you end up with alpha squared t squared equals alpha. You can cancel on alpha from both sides, and then just simply solve for t, and because the alpha is a known value, and that should give you an answer of about 4.47 seconds.